Hi, we are from Group 4 and we're going to walk you through on how we optimize the production of ammonia flow sheet. My name is Rachel.
I am Yangshen.
I'm Vigneswara.
I'm Abigail.
I'm Kian.
We started with optimizing the syngas generation. The first case study performed is to study the effect of the molar flow rate of reformer in combustor steam on the flow rate of hydrogen and oxygen in syngas. The reason for performing this case study is to produce a high content of hydrogen and low oxygen in the syngas, which will result in high ammonia production. As you can see, the suitable reformer steam molar flow rate is 3000 kmol per hour, while the combustor steam is 600 kmol per hour. The next case study is done on operating temperature of the reformer and the conversion of methane in reaction 1. A high conversion of methane is required, and based on the graph, the higher the operating temperature, the higher the conversion rate. Hence, the temperature at 800 degree with a conversion rate of 86.79% is chosen. The third case study is on the operating temperature of the oxidation reactor and the conversion of methane in reaction 1 and 3. The conversion for reaction 3 can be neglected because the conversion rate is very small and has no effect. However, for reaction 1, the temperature at 900 degrees Celsius is chosen because it has the highest conversion of 93.5%. The fourth case study is on operating temperature of the HD shift reactor and the conversion of carbon monoxide in reaction 4. The conversion of carbon monoxide is higher with a low temperature, however a constraint of more than 587 degrees is given. Hence the temperature at the 587 degrees is chosen, which has a conversion of 40.37%.
Case study on operating temperature of LT shift reactor and the conversion of CO in reaction 4 is conducted to determine the optimum temperature and conversion. From the case study, it shows that as operating temperature reduces, the conversion of reaction 4 will increase. We are given a constraint that the operating temperature of the reactor to be lower than 587 degrees Celsius. Therefore, we choose the temperature of 180 degrees Celsius with a conversion as high as 97.54%. For methanator, reverse reaction 1 is desired to remove carbon monoxide, which is poisonous to ammonia synthesis. Therefore, a case study on operating temperature of the methanator and the conversion of carbon monoxide to methane is conducted, and the lowest point of the graph at temperature of 155 degrees Celsius is chosen because it has the highest reverse conversion rate of carbon monoxide. Adjust the ratio of hydrogen to nitrogen in the syngas, and adjust tool is used. The air molar flow rate is adjusted variable and the target variable is ratio of hydrogen to nitrogen in the syngas, and it is set to a value of 3. Now we will compare the molar flow rate of syngas and component molar flow rate of hydrogen and nitrogen in the syngas before and after the optimization. As we can see from the table, the molar flow rate of syngas and the component molar flow rate of hydrogen and nitrogen has increased as the desired after the optimization.
Next, we optimize ammonia synthesis loop as well. First, we did a case study on the temperature of stream 25 and the amount of ammonia that can be produced. As you can see from this graph, highest flow rate of ammonia is produced when stream 25, which is the inlet temperature of plug flow reactor 1, is at 500 degrees C. This step is done in order to increase the conversion of ammonia reactor. Another case study is performed to investigate the relationship between the temperature of stream 32 and the purity of ammonia product produced. Since the desired purity of ammonia is at least 98 mol%, temperature of stream 32, which is the inlet temperature of the separator, is set to be -15 degrees C in order to produce ammonia of purity slightly higher than the target purity, which is 98.77 mol%. In this step, we are trying to maximize the temperature of stream 32 to reduce the usage of expensive methane refrigerant for cooler E107 right before stream 32. By doing so, we are able to save the refrigerant cost. Now we'll compare the molar flow rate and purity of ammonia product before and after the optimization. So after the optimizations aforementioned, the molar flow rate of ammonia increases from 897.5 kmol per hour to 1407 kmol per hour. As for the purity, it increases from 98.73 mol% to 98.77 mol%.
I'll be going through the sustainability part that we tried optimizing for our plant. So we perform heat integration. We perform two heat integrations in order to maximize heat recovery and minimize our energy consumption of our process flow diagram. Here, as you can see, we replace our coolers and heaters with heat exchangers that are circled red. This results a positive and desired effect for our plant by reducing our energy consumption from 6.62 times 10 to the power 8 kilojoules per hour to 4.17 times 10 to the power 8 kilojoules per hour. So perform a case study on the sizing of heat exchangers by taking into account of UA, that is the overall heat transfer coefficient of the heat exchangers, duty of the corresponding heater, and the inlet stream temperature of heat exchanger to maximize our heat exchange. We will take heat exchanger E-108 as an example. From this graph, we will take the intersection point of UA of the heat exchanger and the duty of the corresponding heater, which is E-111 as shown in the picture, to find the optimal inlet stream temperature for the heat exchanger. It is around 703.19 Celsius. From this, we are able to obtain the necessary 3 variables needed to size our heat exchangers, so in order to minimize our wastage of utility and resources. We also clean and recycle hydrogen that is exiting from the purge stream back into the ammonia production section in order to increase our ammonia flow rate. After adding the recycled stream, we can see that the molar flow rate of ammonia increases from 1,128 kmols per hour to 1,559 kmols per hour, accompanied with a drop of the mole fraction of methane. This also guarantees that our purity of our ammonia product does not fall below the market purity requirements.
The overall profitability analysis is evaluated. Initially, the materials and water disposal costs were calculated in terms of the requirements. The raw materials used are natural gas and steam. It is seen here that the cost is lower before optimization. The revenue, which is the income obtained from the annual sales of the products, which are carbon dioxide and ammonia, was marked lower. The profit is obtained by subtracting the materials and water disposal costs from the revenue, gaining a profit value of $18.5 million per annum. The flow rate of steam was particularly low, hence it was increased after optimization, causing an increment in the material and water disposal costs. This forms more products, marking a higher revenue. The profit gain was much higher after optimization, earning about $38.4 million per annum. The utility cost also shows vast differences before and after heat integration. After the introduction of two heat exchangers, the utility cost is saved by almost $600,000. So in conclusion, more product flow rate, purity meets market requirement, more profit. Less refrigerant cost, less cost.
We also recycled the purge, reduce waste and lower treatment costs. We also perform heat integration and reduce our utility costs.
Thank you.